This is the last big section of Calculus 1. Well done for making it this far. Hang in there. You're almost there. In this section, we're looking at integration. What is integration? In short, it's the process of reversing differentiation. In other words, we start with the answer to a differentiation problem and work back to the original function before it was differentiated. That's why integration is also called the antiderivative. We'll look at two types of integrals you need to handle. One, the indefinite integral, and two, the definite integral. How do you tell them apart? Super easy. An indefinite integral has no little numbers, limits above or below the integral sign, whereas a definite integral does. Important, although the integration process is the same, there are a few things we do differently for indefinite versus definite integrals. We'll get to that in a later video. For now, as we start integration, remember this key point. With an indefinite integral, we always add plus c to the answer, but we do not add plus c for definite integrals. I won't bore you with the details of the plus c. In short, when we differentiate, any constant, a number without a variable, drops out. So when we reverse the process, we include plus c to show a possible constant term. There's more on this in my ebook course. For now, just remember, add plus c for an indefinite integral. Don't add plus c for a definite integral. This video will start with the indefinite integral and how to compute it. Once we've covered the method, we'll come back to the definite integral, which we use for practical problems like areas and volumes. More on that later. We're starting the integration video with a warning. It's very easy to get lost in integration, especially about what to do when. You'll find plenty of great resources on YouTube, but if you don't know where each piece fits, they can just confuse you more. You need to see the big picture. Otherwise, this part of calculus will be super frustrating. I got really lost in this section because I couldn't see the big picture, so be patient with yourself. I've put together a game plan I wish I'd had when I was up at 2 a.m. trying to do these problems. Follow the game plan, and you'll see it's much more manageable than it might feel right now. Our game plan for integration is as follows. Step 1, preparation. Do 3 things. 1, split the terms. 2, remove the coefficients, and 3, add x to the power of 0 to every term that doesn't have a variable. Step 2, use algebra to obtain an integration key. Manipulate what they give you so it matches one of our integration keys. This is super important. You must reshape the problem with algebra until it looks like one of the keys you can integrate. You need to memorize these 11 keys. Know their patterns, because they don't change. Whenever we integrate, the problem will integrate into these forms. You'll see I grouped the keys into powers, fractions, and logs to make them a bit easier to remember. There's no shortcut here. You'll have to memorize the patterns, but the more examples you do, the easier it becomes. In my ebook course, I've also included a downloadable cheat sheet you can print and keep next to you while you integrate to make the process much easier. Step 3. When algebra fails. This means we can't, using algebra alone, rewrite the problem into one of the keys. In Calc 1, you'll see this happens in 2 situations, when certain things multiply, products, or when certain things divide, fractions, and we still don't get a key. Products. If 2 things are multiplied and normal algebra didn't produce a key, ask whether there's a differentiation link. If yes, use U substitution. If not, use integration by parts. Fractions. If 2 things divide and normal algebra didn't produce a key, there are 3 options. If there's a differentiation link, use U substitution. If the power on top is greater than or equal to the power on the bottom, do long division. If the power on top is smaller than the power on the bottom, use partial fractions. That's the game plan we'll follow. Very little of this may make sense right now, but we'll go through it step by step. The important thing for now is to have the big picture of the process. In this video, we'll cover steps 1 and 2 only, and then in the next video, step 3. Right? Let's see our game plan in action with an example. We start with step 1, preparation. Preparation has 3 parts, which I've split into A, B, and C. Step A, preparation. Exactly the same as with differentiation. Split the terms. Remember, we split at plus and minus signs as long as the plus or minus isn't inside brackets, in a fraction, under a root, or in an exponent. So we can immediately see we can't split here because it's inside a fraction and brackets, but we can split there. Look carefully that we keep the dx with each piece because the dx tells us which variable we're integrating. Step B, preparation. Remove the coefficient. Here's how we do it. When we have an integral, we can take the coefficient, the number attached to the variable, out in front of the integral. This is an important step because it helps us match our keys. So, looking at the first term, we see the coefficient is 5, remove it, and place it in front of the integral. The second term doesn't have a removable coefficient. With fractions, it's very important to have a 1 over the denominator for it to match our keys. For example, if we had 2 over 5x minus 1, we could remove the 2 as follows. It's very important to check my ebook course where I have many examples of how to remove coefficients. It's all just normal algebra, but it's the kind of thing you don't usually think about, because in normal algebra, we didn't have to remove coefficients like this. Please go through the examples. If you don't successfully remove your coefficient, it won't match a key, and you'll make the integration much harder. For the third term, we have a root. To remove its coefficient, we first split the root. Very important. You may only split the root like this if there is a single term under the root. Once the root is split, we can easily remove the coefficient and place it in front of the integral. The next term is a natural log. Important, for natural logs and ordinary logs, the coefficient is actually hidden in the exponent, because with logs we can move the power to the front. Then it's a coefficient we can remove and place in front of the integral. In the last term, we can see there's no variable, so we leave it for now. Step C, preparation. Add x to the power of 0 to any term that doesn't have a variable, so in this case, the last term. We add x to the power 0 there, and then we can remove the 3 and place it in front of the integral, because the 3 is a coefficient. And with that, our preparation is complete. Our next step in the integration game plan is to use algebraic manipulation to get a key for the integral. Very, very important. My problem must match a key exactly in order to use it, and we use basic algebra to rewrite the integral so that it fits a key. How do we decide which key it fits? Look at the integral and ask, is it something with a power? Then check the power keys. Is it something in a fraction? Then check the fraction keys. Or is it a log or natural log? Then check the log and natural log keys. Looking at our example, we see the first term has a power, so we look at the power keys and we can immediately see, without any problem, that our integral matches the very first key. What we do now is write it in the key. The key says add 1 to the exponent and then divide by the original exponent plus 1. Note carefully that we do not add plus c yet. We only do that right at the end. The 5 that stood in front of the integral now simply stays fixed in front of the key's answer. In our second term, we have a fraction, so we look at the fraction keys to see if we have a match. And we can see that the second fraction key matches, so we use that key as is. In the third term, we have a root, and we can immediately see we don't have a key for roots anywhere. That means we'll have to use algebra to rewrite the root in another way so that it fits a key. If you remember your exponents, we can write a root as a fractional power, so we manipulate it with algebra accordingly. Now we can see we're dealing with a power, and when we look at the power keys, we have a matching key, which we now use as is. The fourth term is a natural log, so we look at the log keys and we can see our integral matches that key, so we use it as is. For the last term, we again have a power, so we check the power keys, match our integral, and use the key as is. Next, we simplify everything we can and obtain the following answer. This is our final answer. So because it was an indefinite integral, we add plus c to the final answer. And you've successfully integrated. Well done. Very, very important. In my ebook course, there are many worked examples to help you integrate, because sometimes you really have to think outside the box with your algebra so that your integral matches a key. Work through the examples. I've included as many steps as possible to make it easy to follow. For the last part of the video, we're going to look at trig functions. The good news is our game plan stays the same. The only difference is that we have separate keys for trig that look as follows. Our job is to match our integral to a key. Here we use our trig identities and reductions to rewrite the integral so that it matches a key. I've also made a summary in the ebook course of the necessary trig identities and reductions that will help you obtain a key. The list is as follows, and if you look at it, you'll see it's the same set of identities you covered at school or in pre-calc. Let's do an example together to see it in action. They ask us to integrate the following. Now, very important. When we integrate trig functions, delay your splitting and removing of coefficients if your trig expression does not fit one of the keys, because you will first need to manipulate the trig function using identities and reductions. In this case, we can see we do not have a key that works with sine squared. We only have a key for a plain sine function. So we look at our identities and reductions to find something that removes the square. If we check our list, as in the ebook, we see under half-angle reduction, there is a sine squared identity we can use to get rid of the square, so we use that. After simplifying the fraction and taking a common denominator, we get the following. Now we see we no longer have a squared trig function, but a plain cosine function, for which we do have a key. As soon as you can identify a key, you can do the normal preparation step. Split the terms, remove coefficients, and add x to the power of 0 to any term that does not have a variable. Once that is done, we are ready to apply our keys. For the first term, we use the usual power key as in the previous part of the video. For the second term, we have a cosine, so we check the keys table and use the cosine key. Doing that gives us the result. We simplify and importantly add plus c at the very end. We have integrated it successfully. To sum up, when integrating trig functions, it is important to know your trig keys. Our job is to manipulate whatever they give us so that it matches a key. To manipulate trig expressions, we use trig theory in the form of identities and angle reductions. The key reminder with trig is do not split too early or remove coefficients too soon. If your expression does not fit a key, check identities or reductions first. If you split too quickly, you may miss the identity or reduction you need. Winging calculus is like winging a parachute jump, fun until the ground shows up. Ditch the 30 open YouTube tabs at 2 a.m. trying to integrate and grab my ebook course, step-by-step fixes and shortcuts. Cheaper than your monthly coffee bill and way easier than explaining a flatlining GPA. Course link in the description. If this helped, smash like and subscribe. See you next time. Cheers!